Okay, so these will just be our only notes for the week. I gave you guys an activity to do in a Dropbox. So I wanted to talk about second derivatives and kind of put it in context of first derivatives in terms of graphs and all that. So a little bit of review. We looked in the last couple videos about where a function is increasing and decreasing. You can tell this by whether the derivative is positive. If it's positive, it's increasing. If it's negative, it's decreasing. So the procedure to find where the function is increasing, I just kind of outlined a review here of the procedure without a calculator, obviously. Let me get a pen. Actually, I can just annotate. We'll try it this way. All right. So to figure out where a function is increasing or decreasing, the first thing you do is find the first derivative. And then you set it equal to 0. You figure out where the derivative equals 0. And today, maybe we're going to talk a little bit about where it's undefined, because that could also be a critical value. A critical value is a potential minimum or maximum. We'll look at that later today. All right, so otherwise we look where the first derivative is 0. Those are called critical values, or where it's undefined. That's also called a critical value. You're going to put the solutions on the number line, and you're going to do a little sign test. The way you do a sign test is you check the intervals between where you put those numbers on the number line, and you check and see them in the first derivative, see if they're positive or negative. If you get a positive number, we can say that the function's increasing in that interval. And if you get a negative number in interval, we can say that it is decreasing. If the sign of the derivative changes from positive to negative, that means it's going from increasing to decreasing. You have a local maximum. And if the derivative changes from negative to positive, it's decreasing to increasing. So obviously that's a local minimum. The one thing to keep in mind when you find the y coordinates, plug the x values you found above back into the original function, not the derivative. Okay, that'll give you a point on the graph. Now, that's the first derivative. The second derivative is the derivative of the derivative, right? And it tells us about a graph's concavity and inflection points. So the first derivative tells you about increase and decrease and relative extrema. The second derivative tells you about what we call concavity and inflection points. The second derivative is written, it could be written with like f double prime of x, or like this, f2 of x, or d2y dx squared. There are other derivatives. I could do the third derivative. The third derivative, I replace it with a triple prime or an f3 or a d3. I could do as many derivatives as I want, okay? But we're just going to focus on the second, all right? So let's talk about concavity. Concavity refers to the shape of the graph. Concave up, I like to think of it as the bowl is holding water. This is the shape that's concave up. Concave down, the bowl is upside down, okay? And if a graph changes concavity from concave up to concave down, or from concave down to concave up, where it changes is called an inflection point. So pretty much if I were to draw a graph, let's just here, okay, something like that. This starts out concave up and it changes to concave down. So about right, I'm just guessing, right? About right here would be an inflection point, because the concavity would change from concave up to concave down right there. If only I could draw something. Here, let's do it this way. Just do it this way. All right, so concave up to concave down, then concave down, it changes back to concave up. So this graph would actually have two inflection points. The deal about the inflection points and why we're interested in them, it's where the rate of change is the fastest. So it's where the slope of the tangent line is the steepest. So I might care about that in business. You know, if I'm buying stock, I might want to buy it when the stock's going up as fast as possible. So that's why I'd be interested in the inflection points. Okay. So, okay, so we can use the second derivative as what determines concavity, all right? So first thing you do to determine concavity of a graph is you find the second derivative, f double prime, the derivative of the derivative. You set the second derivative equal to 0. and you do a number, or where it's undefined, which we'll get to later, but where it's equal to 0, where it's undefined is a potential inflection point. You put the solutions on the number line. So you're going to do a sign test with the second derivative, and you look at the intervals in between your little numbers you put on the number line, and you check them in the second derivative. And if it's positive for the chosen values, we say that in the interval it's concave up. Okay. And if the second derivative is negative in the interval, then we say it's concave down. Okay, so the concavity is all about the second derivative. Where the sign of the second derivative changes is called your inflection point. Okay, whether it changes from positive to negative or negative to positive, it's still an inflection point. And again, to find the y-coordinate of the inflection point, plug the x you found above back into the original function. Okay, so at the end, that's how you do that. All right, so we're going to work a couple examples today, and there'll be a short homework on second derivatives. Not a lot. I know that some of the homework I had to push back because of the math lab blurbs or whatever. So I'm not going to give you a lot because you already have the one assignment too that's up in the thing. Sorry, let me get rid of this. All right, so we're going to work an inflection point and work second derivatives and show you how that works. So what I'm going to do, I don't want to do that. Let's stop that. We're going to go here. All right, so it says find the x coordinates of all points of inflection and find the open intervals where the function is concave up and concave down. So this is all about the second derivative. So I got to take two derivatives. So the first derivative, just using the power rule, would be 4x cubed minus 3x squared minus 6x. And the second derivative, 12x squared minus 6x minus 6. All right, so I need to figure out where that equals 0 to find the places, the potential inflection points. So I'm going to factor a 6 out to make life easier for me. And then I need factors of -2 that add to -1. So that's going to be -2 and 1. So we're going to use grouping. So 2x squared plus blank minus 1. And we're going to put a -2x and a 1x here. Put the factors in there. Okay. All right. So then we're going to group. The 6 just comes along for the ride. So we're going to do, let's see, I can pull out a 2x in the first set. And if I divide by 2x, I'm left with x minus 1. The second set, I can't take out anything, but I can always take out a 1. So I'm going to take out a 1. It doesn't do anything. So you're left with x minus 1. And just like we expect, those factors, they need to be the same, and they are. So this becomes 6 times, let's see, x minus 1, take it out. And behind, you're left with 2x plus 1. All right, so I'm going to set each of the factors to 0. 6 does nothing. So x minus 1 equals 0. So x equals 1 would be one potential inflection point, and 2x plus 1 equals 0 is another. So 2x equals -1. So x is -1/2. And there's no place where this is undefined. He's been asking domain in some of the notes. The domain for all polynomials is all real. So 1 and -1/2 are the points that we're interested in. So we're going to do a little sign test with the second derivative. Make sure you're using the second derivative when we talk about inflection points. So I'm going to do a little table here, x, and the second derivative came out to be this. So it's 6 times x minus 1 times 2x plus 1. So you have 3 regions, 1, 2, 3. So I'm going to pick a number in each one of those 3 regions. So the first region is less than -1/2. I like -1. So I'm going to plug -1 in there. I get -6 times -1 minus 1 times -2 plus 1 So what we have is a positive, a negative, and a negative. So whatever it's going to work out to, it's going to be positive. It's going to be a positive number. All right, so I know it's positive here. All right, so now I'm going to pick a number between -1/2 and 1. I like 0. So if I plug in 0, I get 6 times 0 minus 1 is -1. 0 plus 1 is 1. So I'm going to get -6. So I know that it's negative in that region. And then I'm going to pick a number bigger than 1. I like 2. So I get 6 times 2 minus 1, which is positive. And that's 2 times 2 is going to be 4. That's going to be positive. I don't care what the number is. I know it's going to be positive. So there we go. It's positive. All right. So this tells me that the function is concave up where the second derivative is positive. So remember, this is negative infinity and this is infinity. So it's concave up from negative infinity to -1/2. Or they use a little union here. Sometimes they do, sometimes they don't. It doesn't matter. Or from 1 to infinity. Okay, so that's where it's concave up. It's concave down where the second derivative is negative. So that's from -1/2 to 1. So because the concavity changes both here and here, -1/2 and 1 are both inflection points because the concavity changes sign. Second derivative changes sign. So inflection points would be x equals -1/2 or x equals 1. If I want the y coordinate, I'm going to go back to the original function, this thing, and plug it in to get the y coordinate. Okay. All right, so let's work another example. Interested in concavity. So if I do this, this is for the derivative, first derivative is 4x minus 12, right? And the second derivative would be 4. And you go, but wait, that never equals 0. So what this tells you is that this graph has no inflection points because there's never a place where the second derivative equals 0. In fact, the second derivative is 4. It's always positive. So this tells me that this graph is concave up for all real numbers. And that makes sense because it's a quadratic. If you graph it on the graphing calculator, you're going to see something, I don't know what it looks like, but you're going to see something like this. And of course that's concave up. So it makes the math shows out exactly what you see on the graph. Okay. All right, so we can combine the information about the first and second derivative together to get a pretty good idea of what a graph looks like even without a calculator. Okay, so we have a function here. I want to find the intervals of increase, decrease, and local extrema. That's all first derivative. All intervals of concavity, inflection point, that's second derivative. And we're going to put this all together to get a pretty good graph of what it looks like. All right, so we're going to start one thing at a time. So first thing I'm going to do is the first derivative. So the first derivative is 3x squared minus 2x. All right, so I set this thing equal to 0, and I can pull out an x, and I get 3x minus 2. So setting each of those to 0, I get x equals 0, or 3x minus 2 equals 0. If I solve for x here, you're going to get 2/3. All right. Now, those are places where potential minimums or maximums because we're talking about the derivative. So I'm going to do a little sign test. I like to put my f and my f prime on the same number line that way, or on top of each other. We'll show you in a minute. So 0, and I'll put 2/3 here. Okay, so I need to test the regions in between with the first derivative. Do a little sign test. All right, so pick a number less than 0 for the first interval. I'll pick -1. The derivative is x times 3x minus 2. If I plug -1 in there, x is negative. 3 times negative, the other one's going to be negative. So you have a negative times a negative is a positive. See, I didn't even write the value of the thing. I just know it's a negative times a negative, so it's positive. All right, then I'm going to pick a number between 0 and 2/3. Okay, so this is why I don't care. So 1/3 is a number right between. So if I plug in 1/3 for x, I get 1/3. That's positive. So 3 times 1/3 is going to be 1 minus 2. It's going to be a negative number on the second factor. So it's a positive times a negative. This is going to be negative. And then I pick a number bigger than 2/3, like 1. So if I plug in 1, x is positive, 3 minus 2 is positive. So a positive times a positive is positive. Okay? So this tells me that at 0, the function changes from increasing to decreasing. So 0 is a relative maximum, and 2/3 is a relative minimum. All right? So I'm going to hold on to those points. So I have a relative max when x equals 0. And if I want the y coordinate, I'm going to just plug it back into here. So if I plug 0 in there, I get 0 cubed minus 0 squared plus 4. You're going to get 4 for y. So you have a relative max at 0, 4. Because the derivative changes from positive to negative there. So that's my justification. And I have a relative minimum at 2/3 because the derivative changes from negative to positive. So if I plug in 2/3, I'm going to use a calculator for that because that's going to be gross. I got to plug it into the graph, so it's 2/3 cubed right up there minus 2/3 squared plus 4. And I'm just going to use my calculator because that's a little bit of fraction work, which we don't need to work with too hard. Let's see. 2/3 cubed minus 2/3 squared plus 4, and I get let's see if I can get a fraction out of it. Ugh, it's gross fraction. I'm going to call it 3.85. Okay, that's about as good as. So we have a relative minimum at the point 2/3 3.85. Okay, so that's our first derivative work. Now we're going to work with the second derivative to determine the concavity of this thing. So f double prime would be 6x minus 2. If I set that equal to 0, sorry, I get x equals 2/6 or 1/3 if I reduce it. So this is a potential inflection point because this is where the second derivative equals 0. So what I like to do is line this up with my other sign graph. We're going to do a sign test. So this was f prime. Now we're going to do f double prime. All right, so let's see, 1/3 would fall about right here. So we'll do a little sign test. We have 2 regions to test. We're going to test in the second derivative, which is 6x minus 2. So if you pick a number less than 1/3, I like 0. So if I plug in 0, I get a negative here. And I'm going to pick one bigger than 1/3. I get, let's see, plug in 1. I get 6 minus 2 is 4. So it's positive, right? All right, so the second derivative changes sign there. So that tells me 1/3 is an inflection point because it shows from concave down to concave up. Okay, so what we're going to do is find that point. So I have an inflection point at x equals 1/3. I'm going to plug that back into the original function. Okay, x cubed minus x squared plus 4. So I'm going to do 1/3 cubed. Sorry about that. 1/3 cubed minus 1/3 squared plus 4. And again, I'm going to type that in a calculator. That's not going to be a pretty number, and I just need an estimate of it anyways. All right, so 1/3 cubed minus 1/3 squared plus 4, and we get 3.926. All right, so I know I have an inflection point at 1/3 and 3.926. All right, what this does, it gives me a lot of information about this graph, and if I put these points on there, we'll pretty much be able to sketch all the significant features. So I'm going to make a little table here. So I know that, let's see, there's a relative maximum at 0, 4. I'll plot that. And there's a relative minimum at 2/3. I'm going to give myself a little bit of space, 3.85. So That's kind of pretty close to the other guy, right? Yeah. We'll call this 2/3. Call this 1/3. Call this 1. We'll make this a really kind of stretched out scale. So anyways, and I know I have an inflection point at 1/3, 3.9. Okay, so that's about there. It's in between them. All right. So now the sign test can help me because I know that the function's increasing, looking at the first derivative, increasing until you get to 0 and concave down. So it should be going from the left. This is increasing and concave down. Now, from between 0 and 1/3, it's still concave down, but now you can see the negative f prime. So it's decreasing, still concave down. And at 1/3, it changes to concave up. So it's concave up, but still decreasing. So it's going down, which we can see that. And what happens after that? After 2/3, this function changes to increasing and concave up. So I have a pretty good graph of it. And that's what I expect to see that it looks like. And anyway, so that's my graph. Okay, so you can graph it on a TI 84. I'm going to pull up my TI Smart View. And we'll graph it just to verify that everything that I see, what I see is what I'm thinking I'm seeing. Okay, and I'm going to close the door because you're going to hear my husband. Okay. Okay, hopefully now you won't hear him for a little while. All right, so I'm just going to graph the original function just so we can compare it with what the math told us. So it's x to the, where'd it go? X cubed minus x squared plus 4. Come on, calculator. Well, all right. Well, maybe I'll have to come back to, oh, there it goes. Okay, okay. So I'm going to pull my calculator up, I hope. For some reason, this is being really slow. All right, we'll just stick with a color. So I'm going to clear everything out. So I have y equals x. Oops, I forgot the equation. Let's go back and look at it. X cubed minus x squared plus 4. Okay, x cubed minus x squared plus 4. And we're going to take a look at the graph. Actually, I go to a regular graph. Zoom 6. All right. So one of the things you're going to notice too is it has a little minimum and maximum. When I had that way zoomed out, you couldn't see it that well, but they're definitely there. So we'll go find them. So we'll do second calc. We'll find the maximum, which is 4. And we'll go to the left of the maximum and the right of the maximum. And hopefully it should be at 0.4 like the math showed us. And there it is. This e to the negative 6, this is darn close to 0. It's the calculator kind of spazzing a little bit, but it means 1.6 times 10 to the negative 6. In other words, pretty darn close to 0. And then we're going to go find the other one. Second calc, we'll find the minimum, 3. Oh, okay, I'm to the left of the minimum already. And then I'm going to go to the right of the minimum. Press enter, press enter. And there it is. It's at 0.67, 2/3, 3.85. So it verifies it. Obviously, there's no little button to find an inflection point. There is a way to do that. Just to kind of show you how I can verify the inflection point. I'm going to graph the derivative of this. So what I'm going to do is type math 8, which is the derivative, with respect to x of the function. Now, the way that I'm going to call it, I'm going to go to vars. Y vars a function, y1. So I'm telling it take the derivative of y1 at x equals, oops, at x equals, you have to type x there, otherwise it won't work. Actually, literally x. It's going to take a little while to graph. It's kind of a cheat, but you can see it. So I'm going to go ahead and I'm going to, yeah, we'll just graph it. So what I'm graphing in the red is the derivative. So where the derivative, you can see that it changes signs from negative to positive right around there, right? This would be the first derivative. Oh yeah, that's the first derivative. So we saw the two zeros, 0 and 2/3. We're going to do the second derivative, sorry. So I need to do one more. So to graph the second derivative, actually we could look, well, let's talk a little bit while I've got this up there. An inflection point is where the derivative is a minimum or a maximum. So when you look at the derivative, the inflection point is this minimum right here on the derivative. So you can go find it. Second calc, we're in a minimum. That's 3. We're going to find it on the red curve. So I'm going to arrow down to the red curve. See up or down to switch curves. I'm going to go here, enter. And then I'm going to go to the other side, press enter. And it finds a minimum value of 1/3. Well, it's not surprising because that's your inflection point, right? So that on the blue graph, that's where it changes from concave down to concave up. Another thing you can do, you can graph the second derivative. What I'm going to do is go down here, and I'm going to type math 8. And I'm going to take the derivative with respect to x of y2 now, because that's the derivative of the first derivative. So vars, y vars, function y2, and at x equals x. All right, so this black graph should now be the second derivative. Once it graphs, it's taking a little while to graph. The more of these you do, the more time it takes to graph. And so if we look at that, you see that the black graph is 0 right where the minimum of the red graph is, right? And you can see that it changes from negative to positive, meaning concave down to concave up at 1/3. So what I'm seeing on the graphs is matching what I did with the math. All right, so you can check all this stuff and see that it works. Okay, so that's a little bit with a calculator. Let me do one more example and then we're done for today. I'm going to give you a little Pearson assignment on second derivatives, but not much because I know that we had the others to do. All right, so inflection points in extrema can also occur where the derivative is undefined. This most often happens for you guys with fractions. It can happen with things like x to the 1/2 and all that, but let's just talk about fractions. So basically, when you have one function divided by another, where it equals 0 is going to be a vertical asymptote or a hole. It's going to be someplace where the derivative is undefined. So that is also considered a critical value, and we have to consider them as well. So the best thing I figured to do here was just do an example and show you how all that works. So we're going to work this one. We're going to find the intervals of increase, decrease, minimums, maximums. Then we're going to use the second derivative to find the intervals of concavity and inflection points. All right, so that being said, let's work all the way through this. All right, so to take the derivative, you're going to have to use the quotient rule. So let's see, we have the top is x squared, right? And the bottom is 2x plus 2. So you're going to do the derivative of the top, which is 2x. The derivative of the bottom is 2. Okay? So using the quotient rule, it's the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. So let's plug that all in. The bottom is 2x plus 2 times the derivative of the top, which is 2x, minus the top, which is x squared, times the derivative of the bottom, which is 2, all over the bottom squared. All right, so if I'm going to simplify this to make life easy on myself, I'm going to distribute this through. So I get 4x squared plus 4x minus 2x squared. And on the bottom, we're not going to touch the bottom. We're going to leave it alone. So I can simplify the top. This minus that would be 2x squared plus 4x. Over 2x plus 2 squared. So when I consider critical values, I have to consider where the derivative is equal to 0 on the top, because that'll give you where the derivative is 0, but where it equals 0 on the bottom is where it's undefined. And this is why we have to consider domain, because one of the things you have to remember, by setting the bottom of this to 0, if you go ahead and solve that, you're going to get -1. So what that tells you is you have a vertical asymptote at -1, so x cannot be -1. It's not in the domain. All right, so just keep that in mind as we work the problem. All right, so to find the critical values, I have to test where the top is 0 and where the bottom is 0, okay? Because those are places where the signs of the derivative can change. Okay, so if I solve this, let's say I can factor out a 2x, and I'm left with x plus 2. So I get x equals 0 and x equals -2. And where the bottom equals 0, the square does nothing. Take the square root, it's gone. If you solve that, you get x is -1. So all of these points would be considered critical values, all right, where the derivative is 0, but also where it's undefined. Now, you know that x equals -1 is not part of the domain, so it's not going to be a minimum or maximum, but I still got to test it. All right, so I'm going to do a sign test involving all of the critical values. So I'm going to put them on a number line. And I'm going to test, this splits this graph into 4 areas. All right, so I'm going to test all the regions in between in the first derivative. All right, so in fact, I'll use the factored form of it. This was the top factor is 2x times x plus 2. And the bottom factor is 2x plus 2 squared. The nice thing about the bottom, something squared is always positive, so I don't care what you put in there, it's always going to be positive, so you don't have to worry about it. All right, so pick a number less than -1. I like -2. So the bottom squared, I don't have to worry about it. Just going to plug it into the top. So 2 times -2 is -4. Oh, I can't use -2. That's a 0. What happened here? Oops, I messed up. Okay, -2 should be on there, not 2. I missed the sign. All right, the reason I caught that because the derivative equals 0, and that's a problem. All right, sorry. So we have 4 regions. All right, so we're going to pick a number less than -2 to test. So let's do -3. All right, so 2 times -3 is -6. That's a negative. And -3 plus 2 is -1. So you have a negative times a negative over the bottom, which is always positive. So we don't care about the bottom in this case. So if you plug that number in, plug -3 in there, you're going to get a negative times a negative. Come on, give me my pen back. And we'll just do it this way. Sorry, pen problems. Negative times a negative over a positive, well, that's going to be positive. So I know that this region is positive, down all the way out here. Pick a number between -2 and -1, so -1.5. You don't care what the value is, just if it's positive or negative. I mean, you can plug it in a calculator, but 2 times 1.5, -1.5 is negative. -1.5 plus 2 is positive, and we told the bottom was always positive. So you're going to get a negative. Pick a number between -1 and 0, so -0.5. So 2 times -0.5 is negative. This guy's going to be positive. And this guy's going to be positive. Is that right? Yep. So we're going to get a negative number here. And pick a number bigger than 0. I like 1. And you can plug in 1. You can see everything's going to be positive. Okay. So I've done my sign test. So now I know that there's an interval, the intervals of increase and decrease. So let's get those out of there. The intervals of increase was where the derivative is positive. So that's from -infinity to -2, and from 0 to infinity. Okay. Intervals of decrease would be from -2 to -1 and -1 to 0. Okay, so let's talk about extrema. So the way that I see this, looking at this, we have a sign change here from increasing to decreasing. So -2 is a relative extrema. -1 I do not consider for a relative extrema. This is why domain is important, because x can't be, it's not on the graph, it's a vertical asymptote. So it goes from decreasing to decreasing. Yeah, okay. So, but it's not, and what that tells me, just kind of, it's an asymptote. It's going to probably like go down and then go down here. And then anyway, so that's nothing. And at 0, it changes from negative to positive, so that's decreasing and increasing. So 0 is a relative max. All right, so this is a max and this is a min. And there's my first derivative. Now, I'm not done, because I get to do the second derivative. All right, so the fun thing about all this is that you're not even finished. All right, so we're going to go back to the first derivative. I'm going to go back and look at the second derivative. I'm going to have to clear this. I don't see that I have a lot of choice. All right, so we did the intervals of increase and decrease. Let's see if I can just delete that. There we go. Okay, so the first derivative, I forgot what it was. Let me see, I can undo it. There we go. All right, so things to keep in mind. X can't be -1, so you can't consider it for an inflection point. You can't consider it for a minimum or maximum. All right, so the first derivative is 2x squared plus 4x over the bottom squared. 2x squared plus 4x. Okay, now I'm gonna clear it. Oh, maybe 2x squared plus 4x. Do I have room? Oh, maybe I do. All right, so we'll try it. All right, so f prime, this is where life gets fun. F prime equals 2x squared plus, what was 4x, right? Over 2x plus 2 squared. This is where we're going to have to do a little bit of math when we do that second derivative. So I'm going to do the quotient rule. All right, so the top is 2x squared plus 4x. And the bottom is 2x plus 2 squared. All right, so the derivative of the top would be 4x. And the derivative of the bottom, it's a chain rule. It's 2 times 2x plus 2 to the first, right? Times the derivative of the inside, which is just 2. So you get 4 times 2x plus 2. And I might leave it that way until we see kind of what happens. All right. So we're going to write our second derivative. So it's going to be the derivative of the top, which is 4x, times the bottom, minus the derivative of the bottom, times the derivative times the top, all over the bottom squared. The bottom squared would be 16 times, no, I got to square the bottom, so that means I'm going to square this. So I have 2x plus 2 to the fourth. All right, so one of the first things I notice is that 2x plus 2 is in every term. So you can take one out. All right, so if you divide by 2x plus 2, I'm going to divide every term by that. I get 4x. I'm going to take one away, so I have 2x plus 2 to the first, minus 4. Take that away, so I'm left 2x squared plus 4. And I take out another 2x plus 2, so I'm going to lower that down to the third. So you see, I took it out of every one. That's why I left it factored, so I could see that common factor. You don't want to end up multiplying things out and getting cubics, because that's just going to be gross, gross, gross. All right, so hopefully this is easier to work with. So I'm going to multiply out the top now. So I get 8x squared plus 8x minus 8x squared. Oh, look at that. Minus 16. So I distribute everything through. Guys, make sure you don't miss those signs. That's where you get into trouble. All right, those cancel. So the second derivative is 8x minus 16 over 2x plus 2 cubed. All right, so now I can do sign tests. To do a sign test with the second derivative, I have to consider where the top is 0 and where the bottom is 0. Remember? So the top is 0. If I set the top to 0, I need space. I get 8x minus 16 equals 0. 8x is 16, so I get x is 2. So that's a possible inflection point. The bottom equals 0 if I set 2x plus 2 equal to 0. I'm going to get x equals negative 1. Remember, x equals negative 1 is not in the domain, so it can't be an inflection point, but concavity could still change there. So I need to do a sign test with that. So I'm going to do a little sign test on the second derivative. So here's my second derivative. If I plug in, I ran out of space, so let's just do it here. All right, pick a number less than negative 1, like negative 2. So if I plug it in, let's see, on the top it's going to be negative. It's going to be negative 32. On the bottom, it's going to be another negative. So it's going to be negative over negative. You can verify this on your own. You're going to get positive. Pick a number between negative 1 and 2. I'm going to pick 0. So the top is negative and the bottom is positive. So that's going to be negative. And pick a number bigger than 2. I like 10, positive, positive, so it's going to be positive. Okay, so what this tells me is it's concave up from negative infinity to negative 1, where the second derivative is positive, and from 2 to infinity. It's concave down between negative 1 and 2. And then I'm looking for inflection points. So like negative 1, there is a change, but it's not part of the domain. Remember that the original start of the problem, we decided that x could not be negative 1, so x is not an inflection point. Okay, and we'll take a look at the graph in a minute and see why. All right, at 2, the concavity changes from negative to positive, so I have an inflection point at x equals 2. All right, so that would be a complete analysis of this graph. So now what I'm going to do is plug it in the calculator, and we're going to see what happens at negative 1. You might be interested to see what happens. So I'm going to find my TI grapher again, TI Smart View, and I'm going to plug this graph into the calculator so you can see it. And really, the calculator can help you verify, you know, like everything you found. So that's one of the bonuses about the calculator. Where did I find a maximum at? Where are my maximums? Did I already delete them? Let's see. All right, so I'm going to pull up a calculator. And I'm going to plug the function in, and we'll talk a little bit about what we see. So I'm going to clear everything out. I'm just going to leave this. Well, that's all right. I don't think we need to graph the derivatives. I could leave those there if I wanted to graph the derivatives, but I'm going to leave them off. All right, so clear. So this graph, x squared over 2x plus 2. Okay, y equals. And we're going to hit a fraction, so alpha f1, I want n over d. And I'm going to type x squared over 2x plus 2. If you don't have a fraction calculator that does the fraction bar, please put parentheses around the 2x plus 2 or you won't get the right graph. So I'm going to graph it. So let's kind of see some of the properties of this graph, see what we can see from the calculator. So you can see a maximum there between negative 1 and it looks to be at negative, somewhere between negative 1 and a minimum here. I see a minimum and a maximum, so hopefully I found those. We'll go find them on the calculator. See, at negative 1, it's a vertical asymptote, so that's why it's not an inflection point. The concavity changes. You'll notice that this graph is concave down and this side's concave up, so the concavity absolutely changes at 1. Some other things to notice. What else do we find with a concavity? Well, it changed it too. Concave down to concave up. -1. It doesn't really look like what I graphed, does it? Shoot. Did I graph it right? X squared over 2x plus 2. Okay. Let's see. So what happened? Concave down. Oh, it changes to concave up at 2. Is it just something I can't see? It may be harder for you to see that that's concave. Well, it's concave up, but it doesn't look concave down between -1 and 2. It's concave down there for sure. So we did something wrong. All right, I'm going to stop this video, go back and figure it out, and I'll come back and do it again. All right.